and thanks for the time. I hope you can hear me clear and you can see my screen. So today I want to talk about the Open Hardware Group and what we are doing as RISC-V Cores in industrial quality and open source. First want to talk, can you really use RISC-V to chip it in hundreds of millions of devices? Then I want to go a little bit later and introduce you to Open Hardware Group. And I want to show how we are collaborating in open hardware and how RT-Thread is a very important part of what we are doing. Let's start with if we can really use open RISC-V for commercial shipments. And actually, yes, we can. And we already do. Look at a smartphone, for example. All of you use it daily, and there's already a lot of RISC-V inside. It's not the main CPU and it's not the graphic chip so far, but it's used in the neural processing unit to accelerate your picture working, to accelerate a lot of stuff, but also in the Wi-Fi, the Bluetooth, the modem part. It's used in the touch and the eMMC. So if you're getting a phone, there is a high chance you have a few RISC-V processors already in today. SSDs is another example where RISC-V is already used today. So SSDs actually have a lot of small CPUs inside, and some of them are already RISC-V. The main CPU, which is managing the algorithm, the controller, which is communicating to the outside world over SATA or PCI Express, and then also the NAND flash, which is managing the memory directly. All of this already RISC-V enabled. Now, can you use open source cores or no one is using open source? No, that is wrong. Actually, a lot of people use open source RISC-V cores, but not many talk about it. Especially ASIC design houses like to use RISC-V because of the enhanced flexibility and the adjustability to different scenarios, plus the possibility to add custom instructions. Problem is, they are making a cool ASIC and they're not really talking about it. So here, for example, I have a sample application from one of our friends, Dolphin Design, a really cool design house based in Europe, France. They are offering this kind of processing platform. It's like a microcontroller application. And their customers can order ASICs based on a platform. There are various different things like a DSP processor, power management unit, but also an MCU fabric, audio converter, a lot of things. So if we are looking, for example, only on the DSP processor, the DSP processor inside, there are various different RISC-V cores inside, already available today. Typical application for this RISC-V are IoT, SSD. AI is a very hot topic, especially because RISC-V can be customized to neural networks, can be customized to a lot of things like large language models. So that is really a high flexibility, but also things like audio or connectivity, coming back to the Wi-Fi we had earlier. That is where RISC-V is already used today. Now, the question is, how can you use RISC-V? What are your options? Basically, you do have two options, or you had two options, I should say. The first option, you can license a RISC-V IP core from an established vendor, someone like Andes Technology, or someone like Sci-Fi, Udasip, Syntacore, Cloudbear, Alibaba T-Hat. There are a lot of people who make high quality cores you can license and build an ASIC from it. Now, you pay it and your cost is relatively small as a license cost, but also your possibility to customize the core is kind of limited to what the vendor allows you. If you want to have more flexibility, you can develop a core in-house. Developing a RISC-V core is actually not really difficult. However, you will need to do a lot of verification. You will need to keep updating the core if the specification changes. To make it short, you have higher costs because you need to have more people working on it, but you have a lot of control over the core. In other words, you can customize it as you want it and as your application need it. Now, open hardware, we're filling this gap, this buy versus make decision, and we bring a lot of flexibility with pre-configured cores, validated and verified by a lot of industrial players, but with the option to still modify as you want and as you have to do it. So, Open Hardware Group, we're actually bringing a third option. You don't have to buy it. You don't have to make it. You can take something already ready and verified and then still modify as you need. So what is the Open Hardware Group providing? Let's dive a little bit into our deliverables. The core deliverable of the Open Hardware Group are our RISC-V cores. We do have a family of cores, so 3 members currently, CVE2, a deeply embedded core, CVE4, more a microcontroller unit type, and CVA6, which is a Linux-ready application core. The cores itself are under Apache 2.0 license with Solderpad on top. Apache 2.0 is also used for a lot of software. A lot of companies, especially industrial ones, are well aware of it. Basically, with an Apache 2.0 license, you have a very permissive license. You can take it, you can modify it, you can adjust it, and you don't need to have to tell all the secrets what you're doing. So imagine you're building a product, you can add your secret sauce, and you don't need to tell us what you're adding. However, if you find an issue inside the CPU, you are more than welcome to share it back with us. Also, our CPU is very well verified and there should be no issues inside. It's always possible to find a corner case. Unlikely, but possible. Sharing this with the community helps to improve the IP and make it even better for the next project you may plan. The cores itself are written in System Verilog. System Verilog is a more or less standard in the industry. All the major EDA tools can work with it, so it's very easy to plug it into different projects and work with it. Very important is also a verification model. We're delivering a System 2.0 Verilog-based UVM framework for the course. It's also open source, and it works with various different tools. Because we are a member-driven organization, just like RT-Thread, there are members who are testing on various different commercial tools like Cadence, Synopsys, Siemens Questa, but also on other tools. In short, the open hardware deliverables working with a variety of different operating systems. Now you got a core, you got a verification, you're ready to make your chip. But you know, you need more. You need software. Open Hardware is working on with our members also on the software. So the compilers, GCC of course, or LLVM. So Wei Wu spoke a little bit about this just in the previous talk. Very important for us. But then on top you also have the operating systems. So here you can have a real-time operating system like RT-Thread or various different. There's also support for bare metal, and we are also working on Linux support. For example, one of our members in Open Hardware is Red Hat Group. So the Red Hat Group works on the Red Hat Linux and also on the Fedora, of course. If you go to software, the course and the verification, you still need to have some documentation. So you know how you can integrate and work with all the stuff. Documentation we are providing is also open. It's on Read the Docs. Everything you need is there. And then last but not least, we know that hardware is important for testing, early testing, proof of concept. So we provide some pre-compiled images for FPGA boards so you can test your software, you can test the performance on a standard FPGA board with very minimum investment. And then, of course, you also can have RT-Thread running on it. Now, maybe a little bit about the roadmap. I told you we have basically 3 families. Let me show you the roadmap because there is a lot to these families. First one is the CVE2. It's a deeply embedded core. It can replace finity state machines, can do housekeeping of big SoCs with many cores. It's a small core but quite powerful. Next one is the CVE4 family. Here you can see we have a variety of different cores. Actually, this cores can be used to replace something like an M4 or M33. We have different performance levels, and these cores are verified by a variety of different members. And last but not least, we have the CVA6 family. CVA6 family is an application processor. You can run Linux on it. We're actually also having some coherence project we are working on and a network on chip where you can have 2, 4, 8, maybe 16 cores in a cluster. Typically, that's what you're seeing in AI applications. There's one core I have not been mentioning, the CVW or CV Volley. That is actually from a university, and it's a core related to a textbook. So the Harris and Harris textbook, Digital Design, RISC-V edition, that's what the core they are developing inside the textbook, and they are hosting it here on the Open Hardware Group. Now, there is some very amazing news because they are also working to make this core available in an industrial grade as part of their study course to teach students how to design RISC-V cores for a real application, for an industrial grade application. Just teaching a little bit more than just how to do the core, the pipeline and everything, but also going into the details, what's important for verification. There are a few cores which are under planning, and you can see that we are also targeting something more out of order. So as a member of the Open Hardware Group, you have a say in what we are planning next. You can help to make the decision, and you also can see what are the features needed. Who is the Open Hardware Group, by the way? Well, we're a global non-profit organization. We're registered in Canada, but it doesn't really matter because we're really operating worldwide. And our mission is to host and curate high-quality RISC-V cores and related IP like coherent systems or something to keep several cores together. Really important thing is that it's for industrial use. So we are not hosting any hobby project. We are really depending on our members. We are a member-driven organization to tell us which course they need. And then that's the course we will select. We will verify and host. And by verification, we mean to make it ready for industrial use so you can ship hundreds of millions of cores without having any issue inside. So coming back, the main things we are doing is providing an infrastructure, doing coordination and support with our members to develop, verify, and document in line with best industrial practice. Like I said before, we are driven by our members. Now, the interesting thing is, it's not only industrial members who are really making products, it's also academia and research. That is a great mix because thanks to this mix, we are getting new innovations from research, which then can go directly into industry. We are helping to teach the next generation of students by giving them high quality RISC-V cores, but we're also allowing the industry to have a new test field coming from research, and we are giving research cores which are used in a lot of commercial products. So it's a win-win situation for everyone, and the Open Hardware Group is providing a neutral ground for all these groups to meet, to discuss, and to exchange ideas and start new projects. I just want to go quickly about some of our members we are having here. You can see we have FutureWay, but we also have the Alibaba Group, for example. There is Thales from France, Immerkosen from UK, and a lot of others like the Barcelona Supercomputer, Calray, GroupGets, Cyrus Logic, and so on. In total, there are over 100 members and partners in the Open Hardware Group. We are very proud of the ICAS, which is part of us, but also the BIOS is a part of Open Hardware Group. You can see the Harimat colleague for the teaching material, UC Santa Barbara with the Open Python. A lot of industrial players actually joining the Open Hardware group and contributing actively to what we are doing. Last but not least, we also have our ecosystem with partners. This ecosystem, RT-Thread is a very important partner for us, but we also have people like Cadence, Synopsys, and of course many more helping us in making it a better world. How is the collaboration working and how do you organize so many different academic industry and other contributors and make sure they are all working on the same product? Question. So when you're having an open source collaboration in the semiconductor industry, it's a little bit different than you're doing software. The open source first enable a lot of more possibility to handle things in different ways. For example, you have the RISC-V specification, which is the implementation for your core. But then if you have an open source implementation of a real core, you can get your hands on, you can develop it, and you can test it. Like I said before, we are aiming to have industrial grade open source cores. Industry can use it, but also academic and research can use the same cores for research. They get more accurate data because they're using something which is really used in the industry. RISC-V gives a lot of new possibilities here. And then, yeah, like I said, the collaboration is really nice because industry partners can work on a very specific function for the industry. The industry don't need to give them all their internal source code. They can tell them work with the cores from open hardware, for example, and later implement it in their closed source core. So the variety and possibilities is just much more bigger, and that allows a lot of more innovation. Now, how we are organized? We are organized via working groups and task groups. On top of the open hardware, you have the board of director. They are coming from our top tier members, and they are giving us a clear direction what we should do. They have the last say. The real work and the real decision is made in the technical working group. Technical working group, you can imagine a little bit like central R&D in a company. They're defining what we should work on, and they are defining how we should do the work. Under the technical working group, we have a variety of subgroups. For example, there is one core task group. They are working on the architecture, defining should it be dual issue, how should we solve different problems. There is a dedicated verification task group. Verification is really the most important if you're making a core, no matter which core. So it needs to be verified, verified, verified. No bugs allowed. There is also different groups like the software task group where we are talking about compilers, but also real-time operating systems and other things. The hardware task group is looking for FPGA boards, but also chip implementation, which we are doing. And we are starting recently a safety and security task group because there is a huge demand worldwide. We also have a marketing working group where we are doing webinars like this or engaging with our partners to spread the word about their solution and how they are co-working with open hardware. We have working groups for Asia and Europe just because of the different time zone to make it more easier for a variety of people to join. I just want to go quickly in the course task group and give a short overview how that is working. Course task group is led by some of our members. So Ariane from Silicon Laboratories is the chair of the course task group together with Jerome from Thales. And they are really organizing it, bringing the members together and make sure that we are talking about the same things. The software task group is currently led by Amber Cousin with strong support from the Alibaba group. Here we are defining the software that includes tool chains, but that includes operating systems. The IDE is defined here and a lot of other stuff. There are a lot of variety of different group tasks ongoing, and I want to go into two of them. The first one are the compilers. So we have now the GCC 14.1 compiler is fully upstreamed and is fully supporting one of our cores with custom extension like hardware loops, but also DSP extensions. So the compiler can automatically generate code for the DSP and also for other extensions. The same for the LLVM, and that is done mainly by our members. Another group is the QEMU, where we are getting support for our cores, and then the real-time operating systems, where we have RT-Thread, FreeRTOS, Zephyr, Linux operating system. Here we are having from the Red Hat group, but also Buildroot. Kernel is 6.2 and later, but also previouses will work. So you can see it's a big variety we're supporting to make sure no matter what is your flavor, you will be able to use it with our open hardware cores. IDE is a topic I said before. Here we have Ashling, who took the Eclipse IDE and enhanced it for the open hardware cores. They also included compiler support, in this case from EmberCosm, who is very strong on the compiler. There is debug inside. So if you're getting one of the FPGA images, for example, you have a very nice IDE you can start programming and working right away. By the way, all of this stuff is available on our homepage. So openhardwaregroup.org, you go there, you can find it, you can download it. It concludes actually my talk. I just wanted to give you a short overview about the RISC-V cores we are providing, which we are calling Core 5, how you can use them, and that they are already used in high volume production. Together with RT-Thread, we are very happy to have a good partner to also have a reliable operating system, a real-time operating system, and we would be more than happy if you give our course a chance and maybe even consider joining us as a member. So thank you very much, and to the main stage.
Thank you for the talk. There are a few questions. Are the designs primarily for silicon manufacturers or designed as a soft core?
Very good question. The majority of the course is designed for silicon manufacturing, so for ASICs. You can let them run on an FPGA as a soft core. They are not optimized for it, but they will run and will work. But yeah, if you're making an ASIC, a real silicon, that's the main goal where we are optimizing for.
Is the core optimized for FPGAs, a soft core?
We do have one core which is optimized for FPGA, but to be honest, this core is currently not under development, so I would not suggest to use it. It had a good quality, but the last time we got an update is 1.5 years ago. So I would recommend to take one of the latest cores, and even they are optimized for an ASIC or silicon, you still can compile them for FPGA. You may need a few more lookup tables to do so, but it's possible.
Okay, thank you. Looks so far that these are all the questions.
Okay, perfect. Then thank you very much for having me here. Thanks to Cassie, who is organizing it, but also thanks to you, Niels, for being the moderator. And yeah, I will stay a little bit around, so should you have more questions, feel free to ask me. And if not, give us a connection on LinkedIn or on our website, openhardwaregroup.org. We are more than happy to help you. If you have a cool project that you have been porting RT-Thread or something on our course, tell us. We really like to hear about you. Thank you.